Digo, si graban estaré mejor, ¿saben?
Es que ya estamos grabando, compañero.
Ah, ya me marcó.
Compañero, por favor.
Bueno. Yeah. Hello, we are the team number 3, and we will talk about the evidence of the stage 1. And let's start. First, the first problem is the Pascal. In these problems, we use the simulator, and the problem is the piston 1 have the radius at 30 millimeters and mass of 230 grams, and the piston 2 have the radius at 50 millimeters and the mass is unknown. To obtain the mass, we did the operation force 2 equal force 1 for area 2 and divided by 1. And when the first one is another factor of we need to obtain with the formula force equal mass for gravity. When the mass is point 33 kilograms and the gravity is 9.8. So force one is equal to at 25 newtons. Then we can obtain the first two. Force two equal to at 55 for 0.03 and divided by 0.05. And for 2 is equal 3 at 75 newtons. But we need to find the mass of the piston 2 and we use the formula force equal mass gravity is mass equal force divided by gravity. And mass equal 3 at 75 between 9, 9.8 and mass equal 0.382 grams.
Well, I'm Mauro Pedraza, and I'm going to explain about the problem 2 of Pascal. It says that the piston 1 have the radius at 20 millimeters and mass of 75 grams, and the piston 2 have the radius at 48 millimeters and the mass is unknown. So to obtain the mass, we did the operation. The second force is equal the first force multiplied by the second acceleration divided by the first acceleration. When the first force is another factor of we need to obtain, we use the formula of force that is equal to mass multiplied by the gravity. When the mass is 0.075 kilograms and the grams in 9.8, so for force 1 is 0.735 newtons. Then we can obtain the force 2. The force 2 is equal to 0.735 multiplied by 0.048 divided by 0.02. So the force is equal to 1.75 newtons. But we need to find the mass of the piston 2, and we use the formula force is equal to mass multiplied by the gravity, and it's equal to mass is equal to the force divided by the gravity. It says that the mass is equal to 1.75 divided by 9.8, and it gives us a mass of 0.178 grams. And the Pascal conclusion says that the simulator is a great tool to understand the Pascal's problems, because in there we can change the factors and experiment different situations, and we can imagine how we can use that in the common life. For example, hydraulic systems, elevators, brakes, and the Panama Canal.
I'm Sofia Saray Cruz Cerda, and I'm going to explain the first problem of Archimedes. We have three spheres that have the same volume, 10 centimeters, but they are made of different materials. The first sphere weight is 0.4, apparent weight is 0.3, and a thrust is 0.1. The second sphere is 0.5, apparent weight of 0.4, and a thrust is 0.1. The third sphere, that weight is 0.25, apparent weight is 0.15, and a thrust is 0.1. With the information described in the chart, we can tell that the sphere weight doesn't influence the thrust. If we have the same volume in all the bodies, then we can conclude that the thrust will be the same in the three cases.
My name is Barbara Okiri, and I'm going to talk about the problem number 2 from Archimedes. And then the problem says that the spheres are made with the same material, but each of those have the same volume. So we have to calculate the thrust, and then the weight. Thrust is equal to weight minus apparent weight. So it gives in the first sphere that thrust is 0.1, and in the sphere 2 we have 0.13, and in the sphere 3 we have 0.06. So in conclusion, from this problem, as we say in the previous exercise, the volume is what matters from this. So the different material which each one is made and the weight doesn't have a big importance. We can see here the volume is different, therefore thrust is different in the three cases. Then we have problem 3 that says that they are made from the same material and same volume. So in body 1 is the same as the problem 2. We have to calculate the thrust. So we have the thrust is equal to weight minus apparent weight. So we can see that in the three bodies, the thrust is the same. So in conclusion, we have that is training the same theory as the two problems described before. Now they coincide in the material, weight, and volume. It's kind of obvious that the result is going to be the same for all the bodies because the three share the same data, but again, what defines if thrust coincides is the volume.
I am Javier Garcia, and I'm going to talk about Archimedes, and the problem 4. In this problem, we have three spheres in liquids with same density. The first sphere weighs 0.4 newtons, and the apparent weight is 0.3. The second sphere is 0.4 equal and 0.2 the apparent weight, and the third sphere is 0.4 and the apparent weight 0.35. The thrust is obtained with the formula of weight minus apparent weight. So in the first sphere, that is 0.4 minus 0.3, we obtain the thrust is 0.1. The second one is 0.4 minus 0.2 is equal to 0.2, the thrust. And the third is 0.4 minus 0.35 is equal to 0.05. So we can conclude three spheres with same weight are immersed in different liquids with same density. But these liquids have different density. Thrust change, and it made the different apparent weights among the spheres, because density of different liquids can be more, less, or equal to the density of the spheres. So a change has happened. Now, problem 5. We have a dynanometer that obtain different weights in a different submerged volume. In the first movement, we have 0. So the weight A is 0 and the weight B is 0. The 5 centimeters cubics in the submerged volume, we have the denominator weight A is 0.3 and the B is 0.3. In 10 centimeters, we obtain the same, in 15 equal, and 20 equal. So both weights are the same, so the thrust is 0. For each submerged volume, the sphere weighs the same as before being submerged. We say that the thrust doesn't vary by the depth of the body.
Hi, I am Gisela Sosa, and I'm going to talk about the problem 6. Well, in this problem, we have 4 volumes, 5, 10, 50, and 20. And to resolve this problem, we are going to use the formula that thrust is equal to weight less apparent weight. For this, we have the solution of 0.05 newtons, 0.1 newtons, 0.50 newtons, and 0.2 newtons. In the volume submerged in the water container, it is the same volume of the evicted water. In this sense, dynamometer A weight is less, which is submerged volume, because weight is added for the evicted water of the dynamometer B to its container. And for last, we have our final conclusion. With these tools, physics managed to improve in terms of force and weight. And now, with technology in our hands, it could be more demonstrative. We refer to the use of simulators that represent fictional situations and exemplification of these topics. As advantage, we found the mentioned above. The easy representation of this situation, but also the improve in our knowledge because we are applying and practicing with the use of this displayed data. As disadvantage, we observe the data sacrifice because in the same problems, although it was not so necessary, data was not displayed. It is understandable that we need to find some information, but in this way, we couldn't verify the veracity of these answers, a general problem that can be possible with the use of simulators. And well, thank you. This was our team, and see you later.